we shall have it tomorrow. So let me complete. Let me start. If you want to start this class, so if you desire that tomorrow we shall have this class, I can also start it tomorrow. Otherwise, we
Sir,
shall
it's up to you, sir, because I am the only one here. Or
So what you decide? If you tell other students, you may nobody is today. So if you communicate other
there are
people
many
and
students join. So because of the
late in class.
delay of the time, so they are left.
So let us have this tomorrow. Okay. Wait for 5 to
Yes,
10
sir.
minutes. If they will
Yes,
join,
sir.
then we shall start. Or within 5 to
Yes, sir.
10 minutes, if they will, please have a message in your group because I am not there. So
Okay,
have a
sir.
message in your group that the class is going to be started. Please join. If after then
Sir.
people will join, then we shall start.
Okay,
So
sir.
before that, within 5 to 10 minutes, we shall have the first part of the discussion, which is the preliminary one and very much important to understand the quantum mechanics. Okay.
Okay, sir. I will message.
So in your course, the first thing which is there is de Broglie wave particle duality. So what is de Broglie wave particle duality? Is the screen visible?
Yes, sir.
So actually, everything in physics and other branches of science like chemistry and other, the things can be well understood by classical mechanics, or we popularly call it Newtonian mechanics. So the laws of motion put forth by Newton and the planetary motion and the contribution of Copernicus and others are there, and everything in physics, chemistry, and other branches of science can be well explained by these classical mechanics or the laws of classical mechanics, which I think you have already have in your BSc and earlier in this course. But there is an important experiment which greatly disappointed, and many of the scientists are very much astonished by these results. So what is this? In 1923, a series of notes presented to Academy of Science Paris and a undergraduate student, Louis Dubois, postulated that just as electromagnetic radiation has the characteristics of both waves and particles, all forms of matter should also have both particle and wave properties. And this hypothesis is popularly known as Dubois hypothesis, and I think you know it. So I think I was disconnected. In Dubois hypothesis, your lambda or wavelength of a matter wave is represented by h by p. So why it is called a matter wave? Because Dubois proposed in the year 1923 that every matter have both particle and wave properties. So when the wave properties are most phenomenal, your particle property is diminishing away, and when the particle property is well seen, your wave properties will be distinguished away. And in some region, both particle and wave properties are well observed. So, for example, in your physical world, your trees, your vehicles, trains, aeroplanes, and your cricket balls, your badminton balls, etc. Here, your wave, your particle property is dominated. You never found any wavelength or any frequency or any amplitude of these matter when they propagate. In the other hand, when you have a ripple in a pond or in a sea, you have a tide, the wave property is predominant. And here you can find the wavelength, the amplitude, the frequency are predominantly describes the nature and behavior of the phenomena, whereas the mass, the energy, the velocity of a tide. What do you mean? The velocity of the particles in a tide, the mass of the particles in a tide. This is not of very much importance for a researcher, but the wavelength of the tide, the frequency of the tide, the amplitude of the tide, these are very much important. So the classical world is predominantly the classical world is predominantly occupied by those matters which are in which the either the particle property or the wave property only is predominant. But in microscopic world, you can find that both particle and wave properties can be seen in a matter like that of electron beam, or neutron beam, or neutrino beam, or photon, like these things. So for a photon, you have a wavelength, you have frequency, you have energy. Wavelength and frequency are the wave properties. You have the frequency, you have the velocity, and other things which are having particle property. Similarly, in your electron beam, you know that the velocity is nearly average velocity is nearly 1/10 of the velocity of the light. The mass is 9.11 into 10 to the power minus 31 kg. There is amplitude of the electron wave. There is a velocity of electron wave as C by 10 or 20,000 meter per second, so on and so forth, kilometer per second, so on and so forth. So here both particle and wave properties you can see. And your Debye hypothesis is very much useful to explain the motion and nature of microscopic particles like electrons, protons, neutron beams, and your photons or light ray. And your lambda is the Debye wavelength, which is nothing but a very well-known behavior of any wave. And your h is the Planck's constant, and your p is the momentum. And you can this momentum is very much important when you study a particle. So both wave and particle properties are embedded in one equation. Your particle property is embedded with the expression p. The wave property is embedded in the expression lambda or wavelength, and h is a constant which is there in the equation, and relates these two with an equation. And this expression of Debye explains both the particle and wave properties of a matter wave. Okay, are you getting it?
Yes, sir.
So this is duality. A matter has both the wave and particle properties, but you cannot actually realize these things in a physical world. When you see all terrestrial bodies or matters around you, you have either its particle nature, or you feel its wave nature. But if something is having both wave and particle nature, it is very unusual for you to understand. So for this, you have to you have to take it granted many things which are there in quantum mechanics so that you can understand. And you have to go through the philosophies of our ancient texts, our earlier literatures that that will explain you how something which are contradictory in nature with one another can coexist together, like that of wave and particle. So for this, you may refer the writings of Heisenberg and others who are well versed in quantum mechanics, as well as Vedantic literature and other ancient texts of mankind. So there is a Schrodinger equation. So the quantum mechanics starts with Schrodinger equation, like that of classical mechanics starts with your Newton's equation. So these are the initial things, the matter waves, the Davison-Germer experiment and others, which I shall explain you in the next class, where there will be most of the students, because it is very important to understand quantum mechanics and also the uncertainty principle, the product of two canonical conjugate variables is a constant, and it is impossible to find exactly the values of two canonical conjugate variable, and this is a well-known uncertainty principle. Your energy and time, your position and momentum are canonical conjugate variables, and if you measure the momentum accurately, then your position measurement of position will be totally uncertain. If you measure the position accurately, then momentum measurement will be totally uncertain. This is all about measurement. If you measure the energy accurately, then the measurement of time is very uncertain. If you measure the time accurately, then the measurement of energy will be uncertain. This is basically the philosophy of uncertainty principle, and the product is greater or equal to a constant value. So these I will explain you in detail. So let us have your first expression, which is the basic expression of the quantum mechanics, that is Schrodinger equation. So this I will explain you later on in this course. So now this is Schrodinger equation, one-dimensional Schrodinger equation. So you see, this is a differential equation. This is a differential equation. This 3.13. IH cross del psi by del t, where psi is a function of x comma t, is equal to minus h cross by twice m del square psi by del x square plus v psi, where v is a function of x comma t, and you know x is or psi is a function of x comma t. Your psi is the wave function. Your I is equal to root over of -1, which is a complex number, and your h cross is equal to a constant and related with Planck's constant, and this is V is the potential in the region where we are discussing the behavior of a matter wave. M is the mass of that matter wave, and T is the time. So here you have a differential equation. In the left hand side, the partial differentiation of psi with respect to t, and in the right hand side, this is a second order partial differential equation with respect to x, second order partial differential equation of psi. So your del psi by del t in the left hand side, and del square psi by del x square in the right hand side, and the complete expression is IH cross del psi by del t is equal to minus h cross by twice m del square psi by del x square plus v x comma t psi x comma t. So the force is being exerted by the potential V. So this is the Schrodinger equation in the presence of a potential or in the presence of some force. So your free particle can be expressed as a differential equation where V term will be 0, and you have del IH cross del psi by del t is equal to minus S cross square by twice m del square psi by del x square only. And this is a time dependent Schrodinger equation. time dependent differential equation, because the left hand side is dependent upon time. So if the motion of the particle is independent of the time, then you have only x dependence. So I shall discuss you in detail in course of our discussion. So what is my point of concern is, one way you can express the behavior of a microscopic particle or quantum mechanical particle is to express it in terms of differential equation, which is known as Schrodinger equation. So when you solve it, or you solve some real-time situation like potential well, potential step, hydrogen atom, simple harmonic oscillator, you use this differential equation to solve your real-world problems. So this is one of the approach to deal with the quantum mechanics. And it starts with a differential equation, which is Schrodinger equation. This is for one dimensional and named after Erwin Schrodinger. Similarly, you have three-dimensional Schrodinger equation. I cross del psi by del t is equal to minus h cross square by twice m delta psi v x, where a psi is a function of r comma t, and your v is the potential, which is also dependent upon position and time, and your del, which is del square psi by del square by del x square plus del square by del y square plus del square by del z square. So it is a three-dimensional case. So I think this should be there in your course material, three-dimensional. If not, I shall explain you in my class. I think it should be there. This expression, this del, equation 3.53. Okay. And you see your del square psi, I h cross del by del t is expressed as E, which is energy operator. So this can be also expressed as operators. So del psi IH minus IH cross del by del t can be expressed as energy operator. Your minus h cross square by twice m del square can be expressed as p cap square, where p cap is the momentum operator, b is the your potential operator, so on and so forth. So you know, in my previous class in matrix algebra, an operator can be explained in terms of matrix. So this type of quantum mechanical equations can also be solved by using matrix algebra. And you know, to solve the matrix is somehow easier than to solve by using differential equations. So I think the presentation is disconnected. Let me connect again. So am I audible?
Yes, sir.
So let me connect again. The connection is lost in the computer. Okay. So So you can in the in course of time the screen will be seen here. I have restored the network. So let us discuss. So the another thing is your this is your Schrodinger differential equation, and this differential equation is very much used to understand the quantum mechanics. Another one is you will see the Schrodinger equation uh, can be written in form of different operator formalism, and each operator is nothing but a matrix. So by simple matrix algebra, you can also have all these physical phenomena and behavioral things you can derive. So this is another approach to deal with quantum mechanics, and this is matrix. This is nothing but matrix algebra. So there is a as there is in the Schrodinger equation, there are differential equations. So there are two types of things in a matrix algebra. One is bra, which is the operator that is operated upon a wave function and give you a result. And another is ket. So ket is written in the right hand side, and when it is also a matrix, and this will also give you eigenvector and similar things. And your in quantum mechanics, the eigenvalues and eigenfunctions or eigenvectors, these are the important things, and this gives you the meaning of any solution or any expression, and to understand the physical phenomena thereby. So your matrices like bra operator and matrices like ket operator. So this is basically a bracket operator, and the wave function is in between. So this will help in understanding or having the uh, mathematical part or mathematical calculation in a quantum mechanical system. So as soon as the network is restored, I can show you these things in the screen. So I think there is a network problem. Okay. So your so this is in Hilbert space. The so this is understanding quantum mechanics in a Hilbert space, where there you have the bra vectors, bra notation, ket notation. So this you see this is like a bracket. So your wave function and your the unlike that your differential differential equation in the left hand side, you have bra in the left hand side, and your state function will be in the ket in the right hand side. So a superposition of two or more state vectors of the quantum system is also a state vector of quantum system, and hence an element of Hilbert space. And if your psi1, psi2, psi and all represented in ket notation or state vectors are states of the quantum system, then their linear combination can be represented as shown in the screen. And you can have your quantum mechanics by the algebra of these states and these all can be represented in a matrix form. Okay. So these are all there in your syllabus, and we shall discuss all these in detail. So different type of operator, projection operator, then this is matrix representation of linear operator. So the bra notation, cat notation at the end of the day are having a matrix form, and you have your matrix algebra to solve the quantum mechanics. Your Hermitian operator, unitary operator, you see all these things, eigenvalues and eigenfunction. A cap psi cat is equal to A cat psi. So your A is the eigenvalue. A cap is the operator. Okay. So your psi is the eigenfunction. So similarly, you can have your algebra like this. So this is the characteristics equation. Then eigenvalues of different operators, Hermitian operator, position operator, momentum operator. Momentum operator, when operated upon a eigenfunction, gives you momentum of that momentum eigenvalue of that matter, and this is treated as the momentum of that thing. If energy operator is operated upon a wave function, it gives you your energy eigenvalue. Okay. Similarly, things goes on. Similarly, eigenvectors, which is operated, the eigenvectors of a Hermitian operator can be chosen to be mutually orthogonal, and they form a complete set, so on and so forth. Then they are they are algebra, commutator, unitary, and other things. Then you can see your properties like angular momentum, energy, and other things can be represented in a matrix operation, and observables. Those have eigenvalues. Those are observables, and you can observe those value parameters having its values. Okay. So this is all about measurement of a system, and this will give you an idea how quantum mechanics is dealt with. So tomorrow, quantum dynamics. Tomorrow, this is the Schrodinger picture, which is you can see by using the Schrodinger differential equation, which I have told today in the earlier in this class. Then another is Heisenberg picture. You can see here Heisenberg picture. This is a matrix operator mechanism, or you can have matrices to solve the quantum mechanical problems or microscopic world problems. So you see here there are matrices or operators. Okay, by both the way, Heisenberg equation for a simple harmonic oscillator, choice of basis. You have your simple harmonic oscillator problem in Schrodinger differential equation also. You have they are in Heisenberg matrices form. Okay, so you have all this. So this is the idea how we can deal with quantum mechanics. Okay, so we shall have the detailed discussion to I think tomorrow, where we can have your Schrodinger differential equation and its solution in a simple harmonic oscillator, your potential well, potential state, hydrogen atom, and other real world situations. And in the later on, we shall discuss how to solve all these problems by using your matrix formalism by Heisenberg or operator formalism by Heisenberg. Am I audible?
Yes, sir.
So I think today only there are very less number of students due to I think some confusion. So please communicate to other students also, because our mathematical class, physics class has already completed, and we shall complete the quantum mechanics 1 class as soon as possible. Okay, any doubt in today's class?
No, sir.
Okay. So thank you for your patience.
Thank you, sir. Thank you.
ठीक है, thank you.
Sir, tomorrow will be the class?
From 4 to 6. So today I have some other engagements in our department. So I am a bit late today. Hence today we could not have the two classes which I was proposed earlier. But tomorrow we shall have two classes, one 4 to 5, another 5 to 6. Today
Okay,
there
sir.
is only one class, okay?
Okay,
Because
sir.
of less number of students, I did not have started your second class today. So thank you.
Okay, sir. Thank you, sir.
I think all the course materials are being sent in WhatsApp.
Yes, sir.
Okay. So please go through this, and I shall give you also some of the question papers of mathematical physics in the previous year. Okay. You may go through these and prepare
Okay, sir.
accordingly. Okay. Everybody in the
Okay,
class,
sir.
thank you.